So I'm Brother Guy Consolmagno. I'm the guy whose name is up there. And we just have a few minutes. I wanted to talk about a topic that I think is important for anybody, certainly going into the sciences, but all of us in general in academia to ask ourselves, which is ultimately, why are we doing this? There's this marvelous bit in the gospel that starts out with, "Men of Galilee, why do you stand here looking up into the sky?" It's what the angels are saying to the disciples after the ascension. And actually, that's also the theme of the first sermon preached against Galileo, making that pun between Galileo and Men of Galilee. After all, why are you bothering to look up into the sky with that newfangled telescope of yours? It's both of those senses of looking into the heavens that I want to ask. Why do we do it? What motivates us not only to choose it as a career, but, to get up on a Monday morning and actually go into the lab or into the studio or out to the practice field? My own work is kind of interesting. I've got this fun experiment I do in my meteorite lab. My field actually is meteorites. Those are the rocks that fall from the sky. They give us free samples of the asteroids and sometimes the moon or Mars. And once they fall, sometimes they get collected, and if we're lucky, little pieces of them will wind up in university labs like mine. Actually, they wind up in collections, and the collections are controlled by curators. And curators are kind of like librarians. A librarian's job is to make sure that the books are protected against all those people who want to read them. And the curators are there to make sure that nobody touches the samples. About 30 years ago, when I showed up at the Vatican Observatory and discovered they had this collection, I became my own curator, so I gave myself permission to actually touch the samples and do some experiments. And one of the experiments I wanted to measure was the physical properties, density and porosity, and I could go on forever. In particular, I was interested in heat capacity, one of the many numbers you need if you're going to be doing models. And there are $1 million machines that can take a tiny sliver of a rock, like you see over there, and put it into an enormous machine. It's not quite as big as that. The guy standing next to it is Cyopeel, and he's kind of short, but still. You can make these measurements to a really high precision on a really tiny sample of rock, but the machines cost $1 million, not to mention the people who take care of them every year, because they're always going. You need to hire somebody full-time as an engineer to keep it working. I don't have $1 million. I don't have a full-time technician. And the other trouble is, though these numbers are useful, meteorites are very irregular rocks. One piece can be very different from the other, so you want to have the entire rock, not just a tiny sample, so you get a sense of what the entire rock is doing. And not only that, but even though I am giving myself permission to touch these rocks, even I don't like cutting up my rocks if I don't have to. So, about 10 years ago, came up with this very clever idea. Actually, it was a friend of mine in France who came up with the idea, but he doesn't remember coming up with the idea, so I'll take the credit. The heat capacity is the capacity of a rock to hold heat. In other words, how much heat does it take for the rock to rise in temperature by 1 degree? How much heat is given off when the rock drops in temperature by 1 degree? And here's how you measure it. You take a rock, and you throw it in a dewar, which is like a thermos bottle. This is actually a sippy cup. If you look carefully, that's Buzz Lightyear painted on the side. And you drop the rock in, and you fill it with liquid nitrogen, and the liquid nitrogen slowly boils away, because it's at 200-odd degrees Kelvin below zero. And then you drop the rock in, and the temperature jumps up, or the weight jumps up, because you have this on a scale, by the weight of the rock, but the rock is hot and the liquid nitrogen is cold, so all this liquid nitrogen boils away. And by seeing how much extra nitrogen was boiled away, you know how much heat came out of the rock, because I know how much heat it takes to boil a gram of liquid nitrogen. And that's how I can work out the average heat capacity of the rock. That's great. So what? I mean, I've measured, hundreds of meteorites like this. And I can spend the rest of the talk here talking about them, but why am I doing it? It does happen that scientists can use our numbers when they make models for how asteroids heat up or cool off, or even how asteroids will shift their position in space if they're hotter on one side than the other, and you need to know the heat capacity for that. And asteroids shifting their position might eventually come into an orbit that would cross the orbit of the Earth and, hit the Earth and end all life. And so, yeah, maybe if you're going to be mining asteroids, or if you're going to be deflecting them to save all life on Earth, these numbers will be important. But really, I don't get up in the morning saying, I've got to measure one more rock or else Earth is going to be doomed in 200 years. That's not why we do it. There's another question for why do we do it, though. Why does society support us doing this? To do science requires money and time and talent, and those are as carefully curated as meteorites. Science only happens when somebody's convinced that the science is worth the cost, and that's not something you can take for granted. Somebody's got to decide we're going to be doing this job and not that job. I don't know if you remember the spacecraft that went past Pluto about 10 years ago and took this image. Beautiful, the funny heart-shaped thing there, and it's all very nice. What you don't know is the internal fight that went into that mission getting funded. Because there was a competing mission that would have gone to Europa, a moon of Jupiter, that maybe has life inside it. And the way the guys got the money for their mission to go to Pluto instead of the other guys getting the money to go to Europa is the guys who had the mission to Pluto were in Baltimore, and the senator who was handling the money in those days was also from Baltimore, and she wanted the money to go to her district. We don't do that anymore. After the disgrace of having this sign of, naked political lobbying, the astronomers have set up a new system where every 10 years we get together and hold meetings in rooms like this and argue what are the most important and put together a white paper and show that to NASA, and NASA shows that to Congress, and we hope that's how they make the decisions. Because you see, we're finally going to Europa 20-odd years later. We won't get there with our spacecraft, the ones that have already been launched, until I'm more than 80 years old. I could have found out 20 years ago, 10 years ago, if there was life on Europa, and I won't. And by the time I do find out, I'm going to probably be more interested in, what's for lunch. It's more than just the cost of doing the science. There is another cost involved in doing science. Years ago, I gave a talk at College of Charleston, South Carolina. Kid comes up after the talk and says, that was really great, I want to be a geologist. And I'm going, great, because what I do is geology of the planets. And then he says, but what do I tell my mom? South Carolina, The culture he came from said that geologists are against the Bible. Now, obviously, I don't think that. I've got an MIT ring and a collar here. But a lot of people do think that. His mom thinks that. Even if he's got a more sophisticated idea of Scripture than that, his mom thinks that. Are you going to choose a career that is going to make your mom ashamed of you? Scientists are people. We've got families, we've got desires, we have this mixture of reason and heart, hearts that have reasons that reason does not know. We make these choices based on all of these different forces on us. It's easy to say that people are divided up into Kirk and Spock, but even Kirk and Spock weren't Kirk and Spock. One is not pure reason, the other is not pure emotion. The whole joy of the early Star Treks were showing Spock actually being emotional or seeing Kirk being really clever. I actually got to meet Kirk, William Shatner, long time ago. And I was telling him about being a Jesuit brother and working at the Vatican and being a scientist, and he's going, wait a minute, how does that work? That can't be right. And as we started talking about this, I realized that he had this actually pretty common idea that science is a big book of facts, and religion is a big book of facts, and what happens if the facts in one book doesn't, agree with the facts in the other book? And maybe some of you guys have that idea, because that's the way you've been taught up to now. If you're taking freshman physics, the way you pass freshman physics is to get the answers in the back of the book. And if you've been, going through grade school and high school studying religion, they're going to give you a whole bunch of things that you've got to get right, or you get the words wrong, and then they're very disappointed in you. But that's not science or religion any more than playing scales is playing music. The real science is doing the stuff where we don't know the answers. The real religion is going out and living a life where there is no obvious answer. And science is more than just getting the right answer. Maybe you're familiar with the old issue of, is the planets going around the sun, or do the planets go around the Earth? And part of that argument was, are they in perfect circles or are they in ellipses? Ptolemy, the guy who said all the planets are going around the Earth, knew that planets didn't move smoothly, so you said in order to match the observed position of the planets, you have a circle, and then a circle within the circle, and each circle is going around a circle, going around a circle, going around, and eventually you can match what's going on. And Kepler said, no, if you have the sun in one place and the planets are going around in an ellipse, you don't need all those circles within circles within circles. Which one came up with the right answer? If you mean by the right answer the one that exactly matched the orbits of the planets, it's the guy with the circles within circles within circles, because with that system, you can trace out any orbit, including Homer Simpson. Go on YouTube and look up Ptolemy Simpson, and you can see how you can make this tracing by having circles within circles within circles. It's only ellipses, which are approximately correct because they don't account for the perturbation of one planet on the other, but it's only ellipses that could confirm Newton's law of gravity. Because you see, science isn't just getting the right answer, it's getting an insight into why that answer is the right answer. And even in recognizing that, Newton's laws of physics aren't the last word, that eventually we get relativity to explain things that Newton can't explain. And in the same way, by the way, our faith is not based on rigid certainties. Anne Lamott is a religious writer, and she has a marvelous phrase, swiped actually from Paul Tillich, but she said it much more concisely. The opposite of faith isn't doubt. The opposite of faith is certainty. Think about that. William Shatner was worried about that phrase, blind faith, because he thought that meant closing your eyes and pretending that I don't see anything and just do what I've been told. But that's not what blind faith is about. Blind faith is having faith even when you don't have all the data. And that guy without the beard was me 50 years ago, graduating from MIT. How did I know to go to MIT? I didn't know ahead of time that was going to be the right place for me. Maybe in the long run it wasn't, In an alternate universe, I would have been happier someplace else. Though I kind of liked it there. How do I know I went into the right field? How do I know that, I just being a brother rather than getting married was the right thing? How do I know, how do you know the person you're dating is going to be the right person or not? The school you went to is the right. All of life is making these decisions based on inadequate data, and having the faith that you're going to be doing it right, and recognizing sometimes you get it wrong. The reason I wound up going to MIT was I was actually at Boston College up the road. My best friend was at MIT, and they had weekend movies and, the world's biggest science fiction collection. My entire life was based on a stupid decision by a goofy 18-year-old who I was when I made that decision. Except once I got there, I realized I was happy. I realized this is where I belonged. This was, for lack of a better term, the place that made me content. It's not just that they had weekend movies. They had a life that was exciting as anything in the movies. And you were part of a community. I mean, Lord of the Rings, I want to be part of a fellowship. Hogwarts, I want a hat that will tell me what school I belong in what house I'm going to, and who my friends are going to be. But sometimes it's not that easy. The science I do is finding out cool things, and incidentally, the idea that there's something in one book that contradicts something in another book is not a cause for despair. That's actually what you hope for in science. I've never had the case where this bit of science contradicted that bit of religion, because actually they don't talk about the same thing. But what I do have is this bit of science contradicts this other bit of science, and then I get really excited because I'm about to learn something new, and I can write a paper and, talk about it and maybe even get published. Science is sharing those stories. Science is not, one of the things that drives me nuts in religion is, well, I'm spiritual, but I'm not belonging to religion. And that's like saying, well, I'm scientific, but I don't actually publish any of my results. If you don't publish your results, then what the heck are you doing it for? How will you know that you're wrong or right? How will you have the fun of sharing this with other people? You have to have a community. And that's why you have to have a community of people who are interested in what you're doing. And that is what leads you to this whole need for, will my community, will my society support what I'm doing? I'll just give you an example of what I mean. India has 1.5 billion people. And they've got some mountains. You may have heard of the Himalayas. They got some snow in those mountains. And they got 1.5 billion people. How many medals has India ever won in the Winter Olympics? 0. It's not because they don't have mountains. It's not because they don't have good athletes. It's because they don't have a society of people who will, get their kids up at 3 a.m. to get ice time, or encourage them to learn how to skate or to learn how to ski faster, or will give them other kids to compete against so that they get better, or will give them a place where if they're really good, they could coach the next generation. If you don't have that entire society behind you, you could have all the innate talent in the world, but you're not going to be a world-class athlete. That society supporting you is a big piece of why we do science. We do science because, mom or dad will think that I'm clever if I do this. And I say that kind of cynically, but it actually is important. And there are cultures and subcultures within our society in America that where being a scientist is really encouraged, or where being a scientist is like, why are you wasting your time? You could repair TVs and make good money. As somebody said to a fellow grad student of mine 50 years ago, back when you could repair TVs. But why does an individual do it? When I was young, I was in the Peace Corps. And one of the things, we have a group of 80 of us are all training to be teachers to go to Africa. And one of the things that we used to do in between language classes and teaching classes was to play hacky sack. Maybe you've played this. It's got a beanbag, and you kick it up in the air, you pass it to each other, and you sort of keep it up. It's a sort of feel-good cooperative thing that you'd expect a bunch of Peace Corps volunteers to do. Well, one of the volunteers had her boyfriend from New York come out to visit over a weekend. And he sees us playing hacky sack, and he goes, I don't get it. You don't knock the other guy down? You don't score points? How do you win this game? And it's a legitimate question. How do you win the game of science? Science is like hacky sack. It's this cooperative activity. You gain status by how much other people get from you. You try to keep these ideas up in the air, keep them alive, pass them to each other. So what is your goal? And this is a wonderful comic. I don't know if anybody's ever seen this, PhD comics. I was a PhD student 50 years ago. Nothing has changed. And you can see here, your goals when you first arrive, it's, I'm going to win the Nobel Prize. After 4 years of grad school, it's, I'm going to get to the colloquium in time for pepperoni pizza. Your goals slowly shrink the longer you're there. What are your goals? How do you win this game? Now, if you're a university or a college trying to hire somebody, what are the things you're looking for when you've got 5 different people to choose among? Grants, the Nobel Prize, little prizes, getting your name in the New York Times, having successful students. Maybe that means that you were a successful professor. Maybe the goal is to have academic freedom. I'm such an important scientist that I get to tell NASA what we're going to do next. I'm going to be able to sit on that committee of people writing the white paper. Maybe that's, the fact that I'm successful is that I have more students so I can do more science. But notice what this means. The prize you get for doing science well is they let you do more science. If that's the carrot, then why did I want to do science in the first place? What's the sign of success? Getting a paper in a journal like Nature or Science. So, do you wake up in the morning, jump out of bed, rush to the lab because you're hoping to be one of the et al. Papers, Smith et al., 47 other authors, that's going to tell the world about something new and exciting and groundbreaking about the effects of collective molecular reorientations and Brownian motions of colloids in pneumatic liquid crystals, to quote a paper that I happened to find in Science. Hey, if it was worth publishing in Science, it's probably a pretty good paper. I looked it up. 20 people cited it in the next 3 years. Is that really what motivates you? Is that why you're doing the science? I mean, clearly it's worth doing and it's important to do it, but what are the personal motivations? Is it just because you're curious? You like solving problems? I love jigsaw puzzles, but I'm not sure I'd want to do a jigsaw puzzle solver as a career. How about love? If we didn't love what we were doing, we wouldn't do it. But what is it that we love about doing science? And what's more, you've got these two, the ones in blue are very practical, the ones in red are sort of wishy-washy, but motivate you. Which ones would you give up? Would you give up the approval of others in order to follow your curiosity? Would you give up doing the stuff you're curious about just so that, your advisor or your mom will pat you on the head? If you're hiring somebody, are you going to hire somebody who, brings in a lot of money or somebody who really loves the stuff? And the answer is not necessarily obvious. It also depends on what kind of school you are. Some schools you'd better off getting the one who really loves it because they're going to be frustrated that, King University is not MIT. It doesn't need to be MIT. We've already got an MIT. You need to be the best King University you can be, which means a different kind of faculty. It's very easy to say, I'm going to be noble and follow my curiosity rather than go work for this corporation that has a lot of money. Hey, if you're not being paid, you can't do the work. Let's be practical. What would you sacrifice on list 2 for list 1? Give up the approval of others for your curiosity? Give up tenure to get approval from your family? Give up academic freedom? Give up fame? Or vice versa? Give up grant money to satisfy the truth? Or would you cheat and fake your data to get grant money? Where's your heart? Which is to say, where's your God? And what does that say about the kind of God you're worshiping? What does winning look like? Why do we as individuals choose to do the science? What are we looking for? How do you know when you found it? Internal satisfaction is necessary, but it's not enough. What's the ultimate criterion? Truth, obviously. You know, if you're not going after truth, then the work is meaningless. But that's pretty vague. And sometimes you don't know whether what you came up with was true. I mean, Kepler came up with those marvelous ellipses which led to the truth of Newton's law of gravity. But Kepler was long dead by 50 years before Newton came up with those laws. So it wasn't that kind of truth that was motivating Kepler. Well, let me tell you a story. About 20 years ago, I had a sabbatical year teaching at Fordham University. It's the Jesuit college in New York. And I was teaching the electricity and magnetism class. How many people here have taken freshman electricity and magnetism? Not many of you. You see that t-shirt that I'm wearing? It says, "And God said," and then all of these weird equations, "and there was light." Well, all those equations are Maxwell's equations. A guy named James Clerk Maxwell came up with them in 1865. And that's the equation for how electricity gives rise to magnetism, and how magnetic fields give rise to electric fields, and it's how the change in space of one gives you the change of time in the other with some constants. And so I had gone through for the previous 2 weeks how you derive each of those equations, and I'm writing them all on the board, and then I'm taking the derivative of the one with the derivative of the other and substituting all the pieces, and I've got this one big massive equation on the board. And I'm assuming that my students are all as, glazed over as you guys probably are. Except there's a kid in the front row who looks at the final equation and he goes, "Oh my God, it's a wave." What Maxwell came up with just playing with these equations was that the way that the electric field changes in space is the same that it changes in time, which is what a wave does. I mean, imagine you're standing in a lake and waves are going past you, and you've got a float that's going up and down and up and down and up and down. Then you freeze the lake and you walk from one place to another, and the bob goes up and down and up and down in exactly the same way. That's what a wave is. And Maxwell says electricity and magnetism give rise to what we now call the electromagnetic wave, which is why we've got radio. That's what radio is, which is how you can transmit electricity from Niagara Falls to New York City over long power lines, which is the story behind all of the electronics. Remember, this is 1865. But it's not just a wave. When you take the little bits in all the constants left over and you evaluate them, it turns out the speed of that wave is the speed of light. And suddenly you know what light is. And out of Maxwell's equations, you can work out why I can measure the composition of a star by looking at starlight. You can work out ultimately the beginnings of relativity and quantum physics. They all come out of these equations. And you can imagine the oh my God moment when Maxwell first came up with them. And one of the reasons I wanted to teach E&M is because I remember that oh my God moment the first time it hit me. Oh, it's a wave. And to have the student so on top of things that he could see it before he even gave the punchline. He got the punchline. That was one of the most marvelous moments as a teacher, to say, yeah, I got it there. Every bit of science that I can get from an image like this is a meteorite, by the way, is seen through a microscope. The light waves go in one direction, they're polarized, and then the different colors are twisted as they go through the rocks, and then the fact that this looks like, it's beautiful to look at, the science behind it is beautiful to understand, and the science you can extract about the chemistry of the minerals is beautiful to understand. And all of them give you a little burst of joy. All of them give you a burst of joy. This is a galaxy seen from our telescope. And I could go on for hours about the physics you can get here, but I think you can all see it's just a gorgeous galaxy. This is one of the James Webb images. And another, and another, and another. Each of them is beautiful, and each of them has a really cool scientific story behind them. One that just makes you jump up and down. Because the beauty of the image is just the beginning of the beauty of understanding what the heck you're looking at. The fact that there's a universe at all is fascinating and mysterious. Why is there something instead of nothing? The fact that the universe is rational and reasonable and able to be understood, that is amazing. And the fact that the universe has creatures like us who are inside the universe, able to understand the universe. We are the universe becomes self-aware. Does this mean we're the most intelligent creatures in the universe, or that either there are aliens out there who are smarter than we are, or we are the most smart people in the universe. Either way, it's a sobering thought. That sense of joy is what gets me to go to the lab and day by day collect data points and plot them on here and drop meteorites into liquid nitrogen and find out how each number plots there. Number one, it's fun because I get to handle meteorites, I get to touch pieces of outer space. Number two, I get to play with liquid nitrogen, which if you've ever done is a great blast to play with. And every now and then you get some unexpected result, like the theoretical numbers and my actual measured numbers are a little bit off. Ooh, what does this mean? That burst of joy, that oh my God moment, that's why we do science. Science needs oh my God. I know a lot of scientists who are not sure they believe in God, but they all believe in oh my God, because nothing would happen without that. Thanks a whole bunch.